Okay, so yeah, today we're going to talk about triple integrals, and that is section 5.4. All right, so what I want to do is start by just reviewing a little bit about double integrals. Let's go back and talk about how we did double integrals over general regions, okay? And then we'll see how we can carry that stuff that we learned there to triple integrals. Okay, so you should be seeing the sheet of paper that I'll be writing on. And let's just do a review of double integrals. And we'll review double integrals. In double integrals, we were interested in finding the integral of a function of two variables over a region. Okay. And so we wrote the integral like this. Double integral over R, the region R, with respect to dA. So dA represents some area element. Right? That's a very small little chunk of area. And we multiply the area times the height of the function. What we end up doing is we're finding the volume under the graph of the function, keeping in mind that this volume, when we do it this way, can have a positive or a negative sign. Okay, so the way we figured out these, how to set up these integrals, was by looking at our region and seeing what type of region it was. So your region might look something like this. So let me draw some x and y axes. Okay, your region might be shaped something like this. Okay, that's my region R. And in this particular case, what I can do is I can say that, well, the region goes from between two values of x, right? So it goes from maybe x equals a to x equals b. And for each value of x, if I take any x in that interval, I can find an interval of y's that goes from the bottom of my region to the top of my region. So for each fixed x in this interval, y spans an interval. And if I imagine all these different vertical intervals in this region, I will fill up this region and I will cover the whole thing. And this is what the book calls a type 1 region. That's what a type 1 region is. For each fixed x, I can find an interval of y's. And that will span the whole region if I do this for every value of x. And for a type 1 region, you can set up the integral like this. Right? So I'm going to have my function in here. For each fixed x, I'm going to integrate with respect to y. What that means is that the x goes on the outside. So the outer integral is x. So that's the last thing I do. For each one of those x's, I'm going to do an integral with respect to y. So the inner integral is the dy integral. Now, what does x range from? Well, we said that x ranged from a to b. So the bounds on the outer integral are a to b. And the inner integral, well, that one doesn't just go from a fixed number to a fixed number, right? The place it starts at depends on the value of x. If x is over here, I start this high on the y-axis. If x is over here, I start a little bit lower on the y-axis. And if x is over here, I start a little bit higher on the y-axis. So depending on where x is, I start at a different place. So that means my starting point is a function of x. All right, so this guy down here is going to be some function, I'll call it g1 of x. Okay? And that function is just the graph of the bottom of my region. So I'll just color it blue here. So if I just shade that in blue, that function that takes me from here to here, that is g1 of x. So that's represented by the blue line. And how high do I go? Well, I go to this curve, the height of this curve. Okay, so I'm going to call that g2 of x. That's also a function of x. So that's how high I go. And that is going to be, I'll just shade that in with red. Right? So g2 is this red curve. Okay, so I'm going between two different functions of x. And notice that, as I pointed out in the other lecture when we talked about this material, this variable here, the x, will never be the same as this variable. Okay, they will always be different, and that's very important. The integral won't work out unless that's the case. Okay, so that's a type 1 region. I'm not going to require you to know. I'm not going to ask you, hey, is this a type 1 or a type 2 region or something like that. You don't need to know the names of a type 1, type 2, but I just want to specify that the regions do come in different types. Okay. Now let's just look at a type 2 region. A type 2 region would look something like this. So let's set up some axes and let's do something like this. Okay, so here's my region R. This is a type 2 region. A type 2 region is kind of the other way around with respect to x and y. So for each y in an interval, so y, I can think of y from going from c up to some number d here. So that will span the entire region. And for each y that I pick in here, well, x is going to span an interval, right? So x is going to go from here to here. Okay. So here it's the case that for each y, for each fixed y, I'm going to integrate with respect to x. So what that means is that in my double integral, dy is going to be on the outside. So for y going from c to d, we have one person saying they can't hear me, so I'm just going to let them know. Okay. So let's see, y goes from c to d, and for each y in between c and d, this integral for x, I'm integrating some function here, the x is going to range from here to here. Well, these curves here are functions of y. Right? So I might call the one on the left, this one that goes from here to here, this guy, I might call that h1 of y. And I might call the function that's on the other side h2 of y. So this would integrate from h1 of y to h2 of y. And that's how I would set up the integral for a type 2 region. Now notice this is not a type 1 region, because if I fix an x, say fix x over here, I can't just integrate over an interval of y's and cover this region, because there's a gap here. There's an interval here, but then it splits up and it becomes a separate interval here. There's not just one interval that I can integrate across. I have this problem where there's a gap. And so this is not a type 1 region, it's a different type of region. And there are regions that are neither type 1 nor type 2. Okay, so if I do something like, I don't know, something really crazy, right? Like that, something like this is neither type 1 nor type 2. Okay. This one, though, you can still do it. You could still figure out how to do this because you could chop it up into smaller regions, right? I could maybe cut it right here, and then I have to be really careful about how I do this. I'm not going to chop it all up, but just kind of get you started. I might cut it right there, and I might cut it over here. And what I'm doing is I'm chopping it up into smaller regions where each one of these regions is going to be either a type 1 or type 2. And so by chopping it up, you could actually still use the methods that we had up here to sort out the integral. So it can be chopped up into type 1 or type 2 regions. Okay, so you could still do the integral. You just have to break it up into pieces. It's going to be a little bit tedious, but it's totally doable. Okay. So this is what we were doing with the double integrals. Okay, we were trying to figure out, we kind of thought about what kind of region we had and then expressed the upper and lower parts, or the left and right hand parts, as functions, and then put those functions on the inner integral. Those functions will always be on the inner integral. Constants will always be on the outermost integral. Okay, so what we're going to do today in section, keep forgetting the section number, 5.4, is we're going to do triple integrals. So instead of integrating over a region in two-dimensional space, we're going to integrate over a three-dimensional region, a three-dimensional volume. And so we're going to have a function of three variables defined over a three-dimensional region, and we're going to be integrating that. And for that, we'll need to do a triple integral. Okay, so that is what we are on to today. Okay, so 5.4, triple integrals. All right, so triple integral is, of course, going to have three integral signs. We're going to have some region that we're integrating over. The function is going to be a function of x, y, and z. And instead of putting a dA here, I'm going to put a dV. All right? dA represented a small little piece of area. dV represents a small little piece of volume. All right? Now, dV we will think of as like a little tiny little infinitesimally small cube. Well, maybe not a cube, but a box. It doesn't have to have equal dimensions. And the dimensions of this box, it'll have a dimension in the x direction, that'll be dx. It'll have a dimension in the y direction, that's dy. And it'll have a dimension in the z direction, that's dz. So it makes sense to view dv as dx, dy, dz. Because if I multiply this dimension times this dimension times this dimension, the width times the length times the height, I get the volume of the box. And so that should, these infinitesimal widths multiplied together should give me the infinitesimal volume. So when we did the dA, we saw that we could write it as dx dy or dy dx. Well, dv, you can mix these up as well. And you could write it dx dy dz. You could do dx dz dy. You could do, let's put the dx in the middle. You could do dy dx dz. You could do dz dx dy. And we could put the dx at the end. Okay. Right. There are 6 possible ways to arrange these dx, dy, and dz's. Right? So whereas for the double integral, we only had 2 ways to think about it, dx dy or dy dx. Here we're going to have 6 different ways we have to think about arranging our triple integral. Now, in a lot of cases, there's going to be more than one way that works, so it's not like you have to hunt through all of these to find it, but there are all these possibilities that we will have to keep in mind. All right. So I want to start with an example where we want to find the integral. Let's find a triple integral of, let's say our function is xz plus y. Okay. So this is our function of x, y, and z, right? It's just xz plus y. And I want to integrate this function over the simplest possible thing, just a box. Okay, let's start with something very nice and simple. So where R is the box defined by it's a set of points, x, y, z, such that, okay, now I'm going to give ranges for x, y, and z. So x is going to be between -1 and 1. Y is going to be between 0 and 2. And z is going to be between -1 and 2. Okay. Usually they'd write this in a list. They wouldn't stack these on top of each other. So you have a comma and these would be listed out. But just to save space, I'm just writing one on top of the other one. So I'll put commas here. All right, so that defines a box. So what I'm going to do is I'm going to go to CalcPlot 3D, and we're going to look at this box in 3 dimensions just to get an idea of what we're dealing with here. So here we go. So you should be seeing a picture of a 3-dimensional box. Okay. So I've set it up in CalcPlot 3D to ahead of time to just kind of show you what we're dealing with. So you can see that x goes from -1 to 1. Right? On the x-axis, this box goes from -1 to 1. Y goes from 0 to 2. If I look on the y-axis there, it's going from 0 to 2. And the z is going from -1 to 2. So by specifying those intervals, I'm specifying a box here. So we have some function, our function xz plus y is defined at each point in this box. So take any point in this box, I get a value of my function. Now I can't sketch for you a graph of this function because if you look at the domain here, it's 3-dimensional. The graph assigns a value to each one of those points in that domain. So that's a 4th dimension. So to graph this, you'd need to graph it in 4 dimensions. And that's just, I don't even know. I mean, there are tricks to kind of getting a way to visualize something in 4 dimensions, but I think it's best just to rely on our mathematical knowledge to understand what we're doing. So I can't really draw the graph for you of the function, but knowing what we know from the 2-dimensional case, we can kind of extrapolate what will have to happen here. Okay, so let's go back to the sheet. Okay, so that was our region R. Okay, so when I set up a triple integral over a box, it doesn't matter what order I do these in. If these are all constants, it's not going to matter. I could do any one of these 6 orders, and they'll all work. Okay, so let's just set it up where we do let's do dx, dy, dz, okay? So what I'm thinking of is that for each fixed z, I'm going to integrate with respect to x and y. And for that integral, for each fixed y and z, I'm going to integrate with respect to x. So I'm thinking about what x ranges from. Well, x goes from -1 to 1. Okay? Y goes from 0 to 2. And z goes from -1 to 2. Okay? So first integral is the x integral. Okay, so I'm going to treat z and y as if they're constants, and I'm just going to find the antiderivative of this with respect to x. Well, that's going to be, what, 1/2 x squared z plus, y is a constant, so I just get yx. Right, so this is going to be, I'm leaving those outer two integrals alone, but I've found the antiderivative for the innermost integral. Now I have to evaluate this. This is the antiderivative of this. I'm going to evaluate this from -1 to 1. And then I'm going to integrate that dy dz. If I plug in 1, I get 1/2 z plus y. All right, so let me just save space. I'm just going to write this down over here. I'm going to get 1/2 z plus y when I plug in 1. And when I plug in -1, I'm going to get 1/2 z minus y. And so when I subtract those, the 1/2 z's cancel, but I get y minus -y, I get 2y. So this whole thing just becomes 2y. Okay, so there we go. 2y. Oh, that's dy first, and then dz. Okay. Are there any questions so far? Go ahead and chat or use your mic to let me know. Okay, so the next step, we're going to antidifferentiate 2y with respect to y. Well, the antiderivative of 2y is y squared. So I'm going to evaluate y squared from 0 to 2. And then I'm going to integrate that with respect to z. Well, let's do that on the side over here too. Y squared evaluated at 2 is 4. Evaluated at 0 is 0. So that's just 4. Okay. So this really is just the integral from -1 to 2 of 4 dz. Okay. Antiderivative is for z. Evaluate that from 2 to -1. So I'll just go this way. Evaluate that from -1 to 2. And let's see, that's, if I plug in 2, I get 8. If I plug in -1, I get -4. And so the answer is 12. All right, any questions on that one? Okay, like I said, you could do this one in any order. So you could try it dz dy dx or dy dz dx or something like that. You'll get the same answer every time. Okay. I do want to just point out that I want to think about this like we were thinking about the type 1 and type 2 regions. That's going to be important. When these regions get a little more complicated, we're going to want to think about this carefully. Okay, so let me just sketch the region that we were dealing with here. We said that x went from -1 to 1. So I guess my region went from here to here. Y went from 0 to 2. So I had, on the base, I had this rectangle here, and then z went from -1 to 2. So it's kind of like, okay, that's the region that we're dealing with, all right? So we went up to 2 here. As low as -1 on the z-axis. So when we set up the integral like this, dx, dy, dz, what we're doing when we're working our way towards the innermost integral, we're thinking of fixing a z, and then we're fixing a y, all right? So we're fixing ourselves at a point in the yz plane, right? And then I'm integrating in the x direction, okay? So fix a point in the yz plane. So imagine I'm back here in the yz plane, and I fix a point, right? And then this integral with respect to x is integrating me from here to there, right? It's integrating me in the x direction. Right? Now we're going to do that for every point in the yz plane, right? So when we fill this thing in with these little rays, we will have filled in the entire volume, right? So if you imagine just doing these little intervals all over the place, you'll fill in this whole volume like that. Another way to think about it is that for each z, what we're having, if we pick a point on the z-axis, you're doing an integral with respect to dx, dy. So you could think of that as an area integral. So for each fixed z, I'm actually finding the area I'm integrating over this area within my box. This plane that intersects the z-axis at that number. Okay. And when I do that area, what I'm doing is that for each fixed y, I'm integrating with respect to x. So for every y in that area, so if I fix a y value in here, I'm going to integrate in the x direction. So kind of rewinding it that way is another way to think about it. I fix a z, and that prescribes for me a kind of a sheet, which is a little area. And then within that area, now we just think about it like we were thinking about the integrals in the section involving double integrals. For each y in that area, I'm integrating along an interval in x, right? So you can think about breaking it down in that way. And so we're kind of breaking it down from working from the outside to the inside, okay? And thinking about it that way is going to help us deal with integrals that are a little bit over regions that are a little bit more general. So for instance, what I want to do is I want to look at a region that's not a box. I want to look at, let me pull up CalcPlot3D here. I have another region ready for you. And so, wait, did I do this right? I think I have to share my video. Okay. Here we go. So you should be seeing my browser in CalcPlot3D. Let me know if you're not. Okay, so here we have a region where it's not quite a box. Is everything okay? Can you see this all right? I can never find the chat on this thing. Chat. Okay, let me just. Yes, okay, people are saying yes. For some reason, I can only see the chat when I come back out of the screen share. So I don't. So it should be the main thing that you're seeing. This my browser window here. So here we have a region that's almost a box, but look at the top. The top is not flat, right? It's at an angle anyway. And so we want to integrate over this thing for the next problem. Okay. So for this problem, what I'd like to do is let's think of a function to integrate over this. Okay, well, let's just, oh, right, I remember I had one ready. I had it and I tested it out in Maple. Let me go check. Let's just do the function x, okay? I want to keep it simple so that the integral doesn't get too nasty here. But I want to keep in mind what this region is defined by. The y values are just ranging between 1 and 2. The x values are ranging between 0 and 2. But the z values are not ranging between two fixed numbers. They're going from 0, but they're going up to something that depends on x and y. Now, the surface that I defined here, you can actually look down and how I define this. Z is actually equal to x plus y. So that's what defines this slanted surface that's at the top. Okay? So for this particular problem, okay, this, we're going to do this triple integral over a region. The function I'm going to do is just x, all right? So R is given by the set of points x, y, z, such that we said, let's see, y was between 1 and 2. X was between 0 and 2. Let's start with x. Y was between 1 and 2. And z, now, z goes from 0, but goes up to not a fixed number. It depends on where we are with respect to x, y. It goes up to the plane x plus y. Okay? And so a way to think about that, kind of how we were thinking about that other picture up above. So x is going from 0 to 2, y is going from 1 to 2. And so we have this rectangle in the xy plane. Okay, so if I fix an x, all right, then I can position myself anywhere along this line inside that region, right, by specifying a y. And then I've specified an x and a y. So for each x and y, I can now specify how much my z has to go up. So my z is going to go from 0 to x plus y. So my z is going to go up to x plus y. And that's going to change depending on what my x and y values are. So I get this kind of slanted surface. I don't remember exactly how it was slanting, but I get some, you know, slanted surface up there. All right. So for each fixed x, I did a y, and then for each x and y, I did the z. So when we're thinking about this integral, what we're doing is we're doing the x on the outside, and then the y, and then the z. You work your way outside in like this, okay? The x's were ranging between 0 and 2. So the outermost integral is going to have 0 to 2. Now for each one of those x's, y is going from 1 to 2. So y is going to go from 1 to 2. And then once I've specified x and y, I know that z is going from 0 up to here, x plus y. It doesn't make sense for me to specify this until I've already specified where I am with respect to x and y. Otherwise, z doesn't know what value this is. right? So until I've done the x and y integrals, it doesn't make sense to put this x plus y piece up here. Otherwise, z doesn't know how high to go, right? So you got to keep that in mind so you make sure you get things in the right order. You'll also notice that these variables will never be the same as this one here, all right? And then this variable will never have a z or an x in it for kind of the same reasons. And these will always just be numbers on the outermost integral. All right, so let's unwind this integral and see what we get. So first we're going to find the antiderivative with respect to z. All right, so we're going to go, well, that'll become xz. And then we're going to evaluate that from 0 to x plus y. All right, well, if I plug in x plus y in place of z, I get x squared plus xy, right? And when I plug in 0, I get 0, so I don't have to subtract anything here. So I get this. Now I'm going to anti-differentiate with respect to y. So I get x squared y plus 1/2 xy squared. And I'm going to evaluate that from 1 to 2. Well, let's see. When I plug in 2 for y, I get, let's do that over on the side here. I get 2x squared plus 2x. And then when I plug in 1 for y, I get x squared plus 1/2 x. And then when I simplify this, I'll see 2x squared minus x squared is just x squared. 2x minus 1/2 x is 3/2 x, right? So that's all that is. So I'm just doing the integral from 0 to 2 of x squared plus 3/2 x. All right, and then I do the antiderivative of this with respect to x. So that is 1/3 x cubed plus 3/4 x squared, right? That looks right. 0 to 2. So when I plug in 2, okay, I get 8/3 plus 3, right? Because the 4's cancel here. And then subtract the 0 is nothing. So it looks like it's 8/3 plus 9/3 is 17/3, right? Now we could have done this integral dz, dx, dy. That also would have worked, right? I could have started it by fixing a y and then integrating with respect to x going this way and then asking, okay, well, for each point in there, how high do I go in the z? But what has to happen is that z has to be the innermost in this problem, because z is the one that's determined as a function of x and y. That's what determines my height. And so we need z to be on the inside. And in fact, whatever has the most variable, whatever's determined in terms of the most variables has to be the thing on the innermost part. And the thing that is determined in terms of the fewest variables, in this case both x and y, they're just determined by numbers, can go on the outside. So the fewer the variables you're determined by, the further out in the integral you're going to appear. Okay, so let's do another one that gets a little bit more hairy, where we can't just flip the x and the y, where we're going to have to be really more careful about how we set it up. Okay, so what we're going to do is we're going to find the volume of something that's almost a tetrahedron. Okay, so find the volume. I'm just going to draw a picture of it. Here's x, y, and z, and it's going to be where this plane intersects the first octant of the x, y, z coordinate system. So when you intersect a plane with an octant, you get a triangle like this. So let's say that this is the plane 4x plus 3y plus 6z equals 12. Okay. And what I want to do is find the volume inside of there. So you see you get this, it's kind of like a tetrahedron. It is a tetrahedron. It's not a regular tetrahedron. Not all sides are the same dimensions, but it's a four-sided figure where each side is a triangle. Okay. And I want to find the volume. Well, volume is obtained by integrating a triple integral over the region. What would I integrate? Well, remember how we did area, we just integrated the function 1. So to find volume, you just integrate the function 1. And that should make sense, because if you integrate dv, you should get v. If you sum up all the tiny little volumes, you should end up with the total volume. That's what we're doing. So this is all we have to do. Our function is just 1. The tricky part to this problem is figuring out how to specify the bounds on this one. And you can actually set this up dx, dy, dz, dz, dy, dx, any one of those 6 ways. Oh, wait, I'm getting the question here. Oh, can you please repeat why you put 1? So one way to think about it is that if you just integrate dv, you will always get v. If you integrate dA, you always get A. So if you integrate dV, you get the volume, the total volume. If you integrate dA as a double integral, you get the total area. If you integrate dx as a single integral, you just get the total x length. So that's kind of just the way integrals work. The other way to think about it is, well, I know when we did areas, we mentioned that. Let me get another sheet, because I don't want to mess this one up. I don't know how satisfying this answer will be, but the area of, so when we did areas, we said that the integral of, the area is given by of a region is given by the double integral of the region of the function 1. And the reason was, if you imagine this in 3 dimensions, if you have some region down here in the xy plane, this is my region R, I can actually think of its volume. And I can think of a volume by just extending this region up 1 unit. Right? So if I just make the height of this 1, I know that the volume of this thing is equal to the area of the base times the height. Okay? So the volume is equal to the area of R times the height, which is 1 in this case. Which means the volume is the same as the area when the height is 1. Okay? And we said that to find the volume under a graph, you just integrate the function. Right? So on the other hand, the volume is the integral of the function, but the function is just is just constantly equal to 1. That's how you get this graph that's up here. It's just a flat plane, a constant height 1. So we know that to find the volume, we integrate 1 dA. So therefore, tracing this backwards, we see that the area must also be this. Okay, so now just extend this, kind of do the analogous thing. If I want to find, if the area is the integral of 1, then it only makes sense that if I want it in 3 dimensions, if I want to do the volume of something, it would also be integrating 1. So those are kind of 2 different explanations. Okay, so we want to find the volume of this thing. We want to integrate this. How do we set up this integral? Well, pick a variable to start with, okay? I'm going to say, let's start with x, okay? So I'm just going to pick an x value here. And now for each x, I'm going to integrate this. I'm going to find, I can specify different values of y by integrating in this direction, right? So for each fixed x, I can let y vary from here to here, right? And then for each of those y's, I can go from here up to the top. And I'll get to every point inside this tetrahedron if I do that. For each fixed x, I let y go from here to here. And then for each fixed x and y, I let z go from here to here. And that will get me through every single point in this tetrahedron. So that's one way to set up this integral. We started by, I'm going to leave some space here because I'm going to put some stuff up here. We started by fixing x. So x goes on the outside. Okay. And then for every fixed x, we integrated in the y direction, right? So y is next. And then for each fixed x and y, once I had those figured out, I got to this point, I integrated in the z direction. So z is last. So you work from outside in. Now, what are we going to put in these bounds? Well, x is the easiest. What values of x do I do this for? Well, I just have to figure out where I started from. Well, that's clearly x equals 0. And then I have to figure out where I ended at. So what is this point? Well, we can figure out what point that is because that's the point when, if I just look at it, I'm on the x-axis. So that happens when y and z are 0, right? This is not really even a calculus problem. It's just an algebra problem. You know, what point is this on this, according to this equation? Well, I'm on the x-axis, so y and z are 0. So that just says 4x equals 12. So x must be 3. So x goes from 0 to 3. Okay. That's the easiest part. I can also figure out what these points are, because at this point, x and z are 0. So I just solve that equation. I get y equals 4. And this point is when x and y are 0. So that's when z is equal to 2. So I can figure out what these intercepts are. Right? And now I can figure out what the bounds for this integral are. Right? It starts at 0. Y starts at 0, so I know I can put 0 down there. How high does y go? Well, y goes up to this line. All right? Well, this is not going to be a constant, right? Because it depends on x. Depending on what the value of x is, I go a different distance. So we have to figure out what function of x this is. All right? Okay, let's figure that out. So let's look at this graph in the xy plane. So let's just take it down here. X and y. Oops. And I'm just going to draw that line. It had y-intercept 4 and x-intercept 3. Right? So that was the line that I was looking at. That's the same thing, just looking at it from above in the xy plane. So what function of x is this? Well, this is pretty easy because it's a straight line. Its slope is -4/3, and its y-intercept is 4. So there it is. So that is what this line is represented by. And that's how high y goes. So what I'm doing is I'm really going from, when I fix an x, y is going from here to here. Right? So it's going up to this height. So that's what I put here, -4/3 x plus 4. Now, what about the z? Okay, so once I've specified those, I need to see how high to go. Okay, well, I'm going to start at 0. That's clear. I start down here. How high do I go up here? Well, that's determined by the height of this surface. Okay? What's the height of the surface determined by? Well, here's the equation right here. Just solve this for z. Okay? So if you solve this for z, you get, let's see, we'll subtract these things from both sides and then divide by 6. Right? So that's the height that we have to go. So that's the thing that goes over here. All right, so I'm going to have up here, I'm going to have 12 minus 4x minus 3y over 6. That's the bound, upper bound on the innermost integral. Okay. And we can figure out this integral. I'm not going to go through all the steps of figuring out. I see there's fractions. It's probably going to fill up an entire sheet of paper if I try to do it here in big, writing big so for the screen. So what I'm going to do is I'm going to go to Maple and do it. All right. It's not a hard problem because I think these functions are just, they're all linear, right? So that it's not difficult. It's just, it's going to take up, I'm running out of paper over here. So what I'm going to do is I'm going to take you to Maple. And we're going to work it out there. Okay. And by the way, even if you don't have Maple installed on your computer, if you have a computer at home, you can access Maple through, I posted a link, there's the virtual, you can use Maple on a virtual server over at Queensboro. And you can still use it that way. I tried it out, it works pretty well. Okay, so what was the integral we were doing? Well, we were doing a triple integral, so I'll just grab triple integral with bounds over here. Oh, am I sharing my screen? Yeah, okay. Triple integral of bounds over here. We said that the, oh good, it's even set up in the order that I set it up in. How nice. I lucked out there. The x went from 0 to 3. 0 to 3. The y went from 0 to negative 4/3 x plus 4. And the z went from 0 to, then we had that fraction. 12 minus 4x minus 3y all over 6. The function that we integrated was 1, right? And let's see. Make sure that you got dz, dy, dx. You may need to change those orders if necessary, but it's set up right. Oh, wow, look at this. Maybe we could have done it by hand if it came out that nice. The answer is just 4. Right, not too shabby. Okay. So you should, as an exercise, go through and do this by hand. It looks like it'll be pretty, it'll come out all right. Okay. Okay. That was setting up the integral dz, dy, dx. I just want to set it up. It turns out you can set this one up any one of the 6 ways, right? I want to set it up one of the other 2 ways, just one of the other 6 ways, just so that you can kind of see how that would play out. All right. So let's do the same thing, but let's set up this integral. With respect to, in a different order, all right? So, where are we here? Okay. Let me just, let me redraw the picture. Let's just start again. All right, so we got z, x, and y. We know we intersected here at 3, 4, and 2. And that gave us this tetrahedron. And the surface was given by this. All right. So suppose I wanted to do, let's really mix it up. Let's do dx, dz, dy. How about that? Now I know I need to leave space here because I got to write those functions up here. So I'm going to do, I said dx, dz dy. All right. So here I'm starting with my y. All right. So start with a y, and then ask yourself, oh, what am I doing next? I'm going z. So I'm going in this direction. I'm going up in the z direction. So for any fixed y, I'm going to go up here. I'm going to integrate with respect to z. And then as I move along this line, I'm determining a y and a z. So then for each fixed y and z, how far do I come out in the x direction until I hit this surface? That's how we're doing it this way. Okay? So what does y range from? Y goes from 0 to 4. Okay? Now, for each y between 0 and 4, how high does z go? Well, that depends, because it depends on what y is. This is not a horizontal line, it's a diagonal line, so it depends on the value of y. I need to find this line as a function of y. Okay, so what is that? Well, its z-intercept is 2, and its slope is down 2 over 4, so -0.5. So in the y-z plane, right, I'm just going to draw that line again. It just looks like this. Z is equal to -1/2 y plus 2. Just mx plus b, except it's my plus b because it's y is the variable. So for each fixed y, that is how high I have to go. Okay, so z, let's go back down to the integral. Z is going to go from 0 up to this high, -1/2 y plus 2. That's moving up along this line segment in the back. So now, as I move along that line segment, I've specified both a y and a z. So now I have to ask, how far do I have to go out in the x direction? Well, I have to go from 0, from all the way in the back, up to until I hit this surface up here. Well, that surface is given by this equation over here. So I want to know how big x gets, so solve this for x. If I solve this for x, I get, let's do that up here, I get 12 minus 3y minus 6z over 4. Right? Yeah, that looks right. So that's how big x gets. So x is going to go from 0 to that. Right? So it's going to be 12 minus 3y minus 6z over 4. That is an alternative way to set up this integral. That will also get me the same answer. Right? That'll also get me 4. And in fact, this region is such that it's just a super nice region. It's not super nice, I mean, it's a little bit complicated to set it up, but it's nice in the sense that you can do it in any order. It doesn't matter what order you set these up in. You'll be able to find the corresponding functions that go here, here, and here. Okay. Let me look at one more. Let me ask if you have any questions first. Any questions on any part of these? I'm going to look at while you're thinking about questions, I'm going to look through the book here and see if I can find some exercises that might be a little interesting to look at. Yeah, this one here. Okay, can you please repeat why you put, oh no, that was an old question. Okay, I didn't see any questions here. So what I'm going to do is copy down this problem from the, I just found it in the book here. Can you all see the paper? Is that what you're seeing? Yeah, okay, cool. Let me just copy this down. So we're going to do this integral, and the region is going to be, okay, x is between 0 and 1. Y is between 0 and x. And z is between 0 and 5 minus x minus y. How would I set this up? Without even looking at the picture. But we will consider what this actually looks like after we're done, okay? Just by looking at this, I can see that some of these have variables in them and some of them don't, right? So if they don't have any variables in them, it's safe to put them on the outside. Okay, so just by seeing this, I know that I should put x dx should be on the outermost part of this integral, all right? So when I set this up, I'm going to put dx as the last thing I do, because it just goes from constant to constant, 0 to 1. Okay. And then I look through these bounds some more, and I say which one has the second, or what should I say? Not the most number of variables, the least number of variables involved in the bounds. Well, it's this one. See, this one only has an x in the bound. This one has an x and a y. So this one is the next most simplest range of values. So it's going to go next. So my y is going to be the next thing I integrate. And those bounds are 0 to x. And then the most complicated one is the z. So that's the one I should put on the inside. And it goes from 0 to 5 minus x minus y. Okay. So that's how I would set this one up. Kind of put the simplest stuff on the outside, the most complex stuff goes on the inside. If two things were equally as simple, you could put them in either order. It doesn't matter. Okay, so so what would you prefer to do? Look at more how to set integrals up based on this description, or work out the details? Somebody text me or shout out something here. Set up. Okay, I agree. Okay, so before we do the next one, I just do want to draw a picture of what's going on here. I think that might be useful to see. I haven't done this one ahead of time, so I hope this works out okay. Look at what's happening. The x is going from 0 to 1. All right, so x is going from 0 to 1 over here. Oh, off the screen. Y, now, so once I've specified an x, y is going from 0 to x. Okay, so what's the line y equal x look like? Well, it's a line that kind of comes down this way. So for each x in here, y is going from here to here. So I can see what I'm doing. So the base of this region that I'm dealing with looks like this. It's this thing. I can see that just by looking at the first two lines. And then once I've specified x and then y, I'm going to find myself somewhere in here. I've got z. Z is going from 0 to this. Well, this defines a plane. All right. So in fact, I can see when I plug in x and y, I get equals 0. I get 5 for z. So actually, went over here. I know it intersects the z-axis at 5. And I don't know. I can even try to find the intercepts of this plane. I don't know if that's such an interesting thing to do. Yeah, I mean, when x is 0, it's the line 5 minus y. So the plane, I don't know how easy that's going to be to sketch. So let me just say it's some kind of flat surface up here because it's a plane. So my region is, my volume is probably going to look like this, something like this. I may have it angled in the wrong direction or something like that, but this is the rough idea. So for each fixed x and y, I'm going to integrate in the z direction until I hit this surface. So I'm going to go from 0 up until I get to that height. And this height depends on both x and y, because depending on where I am in here, I have a different height that I have to go. So I can kind of get an idea of what it looks like just by reading these off. Okay. Okay, so let's, I'll go fish out another problem from the book. Let's get something that's a little more interesting. Oh, this one looks interesting. Okay. So this is number, am I on the screen? Yeah. Number 197 in your book. It says to do the integral. Notice they give different names for your region. In the book, they like to call it E, I guess. I was calling it R for region, but it doesn't matter. It's just a variable representing something. Here, the region E, they say, is the set of points x, y, z such that, okay, it says -1 is less than or equal to x is less than 1. Y is between 1 minus x, negative root 1 minus x squared, oops, to positive root 1 minus x squared. And z is between 0 and 1 minus x squared minus y squared. Okay. Sorry, I squoze things in a little tight there. I was a little sloppy. So what are we gonna, how are we gonna set up this integral? Okay. Well, which one has the simplest bounds? It's the one with the x, right? So again, for this problem, I want the x integral to be on the outside. So my outermost one is x. And then what's the one with the next simplest one? It's the y. It's only got one variable in its bounds. So then I would do y. And then the one that's got the most complicated bounds is the z. So it looks like it's dz dy dx again. And it's just based on which bounds are have the most variables in them, right? Now, what does x range from? Well, x goes from -1 to 1. These should always be numbers out here. It's possible for them to be variables, but that's because the variable shouldn't have to do with what you're integrating over. It should be something else in the problem. So it shouldn't be one of these variables, right? Though none of these variables should appear out here. Okay. Y, what does y range from? Well, it goes from -1 minus root 1 minus x squared to positive root 1 minus x squared. And what does z go from? It goes from 0 to 1 minus x squared minus y squared. Okay. And that's how I would set up that integral. It might be useful to see what that region might look like. So let's just sketch it out. I think it's good exercise to do that. And it's a good thing to check just to make sure that things are making sense. Maybe I should have thought this through before I drew those axes because I see I have to go back out here this way. And y is going to have to, I'm going to have to go out in this direction a little bit. Okay, so I see that x is going from -1 to 1. So x is ranging from here to here. Y is ranging from this value to this value, right? So these should look familiar. You should recognize what graphs these are. This comes from the unit circle. If you solve x squared plus y squared equals 1 for y, you get these two functions, right? So these really just come from the unit circle. So y is going from the bottom half of the unit circle up to the top half of the unit circle. So for each fixed x in between -1 and 1, I'm going from here to here in the y direction. And that's how I'm specifying my x's and y's. Okay. And then for each x and y that I've specified, I'm going to go in the z direction. Now, z looks like it's 1 minus x squared minus y squared. This is a paraboloid opening downwards. It looks like what I'm getting here actually, when x squared plus y squared equals 1, z is 0. So I'm actually getting the paraboloid that actually looks just like this. So actually, it's exactly just, we're just integrating over the top half of this paraboloid where the paraboloid lies above the xy plane. That's really all we're doing. And so y is going to go from here up until I hit this surface. So I'm really just filling in this bowl-shaped region, and that's the volume that I'm integrating over. You don't need to see this picture to set up the integral. We could have done the complete integral without even looking at that picture. But I think it's really good to see the picture, and I think what'll happen is sometimes you'll just be given the picture and you'll have to figure this out, like we did in one of the previous problems. And so it's good to be able to go back and forth. Okay. Sometimes they'll just give you a picture. Sometimes they'll give you the integral set up. Let me just see if there's another type of problem here. We'll do one more. I'm going to find one that's a little more interesting. Okay. Yeah, this one looks good. Okay, so we'll do number 201. I think I can squeeze it in here. Okay. I gotta conserve paper these days. 201. Okay, in the book. They want to do the integral over this region. They're going to do, it doesn't matter what function I put in here because we're not going to actually do the integration, but this is what they want us to do. The region is the set of all x, y, z such that they say that x is between -y to the 6th and square root of y. Y is between 0 and 1. And, oh, wait, no, sorry, they did write a 1, but then they put an x next to it, so I'll just write x. And then z is between -1 and 1. So that's what we have. Y is between 0 and x. Okay. All right. Well, when I set up this integral, which is the simplest? Which one has the simplest bounds? Well, in this case, it's z. Z's bounds are just constants. So in this case, z should be on the outside. And z is going from -1 to 1. Which one's bounds are the next most complicated? Well, these both look kind of equal, right? You know, this y is in terms of a single variable x, and this x bounds are in terms of a single variable y. So it actually doesn't matter. I could do this dy next and then dx, or I could do dx next and then dy. So let me do it both ways. Let me put dy next. So y goes from 0 to x. Now that I think about it, I think I may have been wrong about that. I see a problem. Let me point out what's wrong. Let me put the x in here, and oh boy, you know, I think it may have been a typo in the book because it says, yeah, I think this is actually a typo because this is going to be complicated if it's like this. Let me show you what's wrong, and then we'll fix it, all right? So look, what will happen if I integrate with respect to y right now? I'm going to evaluate the integral at x. So I'm going to end up with an x in my answer. And then I'm going to go to the integral. My last integral will be with respect to z, right? And then I'll integrate out the z's, but I'm still going to have an x left over. So I'm going to get an x in my final answer, which doesn't really make sense. We should be integrating this function over a volume. We should be getting a number as an answer. So I can tell something really weird is going on here. In the book, they wrote 1x, and what I'm thinking is that they meant to just write 1, and the x was a typo. So let me fix that. Let me change this to a 1. I picked the most interesting problem, and I guess it was interesting because it was actually messed up. So really, that was a 1. So really, I don't think I should have set up the integral this way. Let's undo this. All right. But we can definitely put z on the outside, -1 to 1. Y should go next because it's also simple. It's in terms of constants. So 0 to 1. And then the x is a little bit more complicated. It's in terms of a variable, y. So x is going to go from -y to the 6th up to root y. That's one way to set it up. We also could have reversed the y and the z because they are both just determined in terms of constants. So we could just flip those around, right? So I could have done it this way as well. These will both work, right? But what is important is that the x is on the inside because it's got the bounds that are in terms of the variables that we're going to be dealing with next. You don't want to deal with those variables and then have those variables appear again in the bounds. Otherwise, you're not going to integrate those things out. So if a variable's in the bounds, you better be integrating it out later on. So x has to be done first. But the other two can be switched around because these are just constants. All right? And I'll let you work it out. I'm not going to go work this thing out. You could work it out and check it on Maple to see your work, to check your work. So I think I'm going to stop there. I think we've talked about a lot of stuff. I've posted the homework assignment that deals with this. I forgot what due date I set for that. But you can check it on My Open Math, so you should go check out that assignment. Are there any questions about things we talked about? No. Oh, the bounds for the final problem? Yeah, what about them? I can go through it again. So, you know, the most complicated bounds, the only one that is determined by variables is the x. So that means that the x has to be on the inside, right? If the bounds are determined by constants, they can be the outermost integrals. You can always just do those on the outside. If they're constants, it doesn't even matter what order you put them in, because they're equally as simple. So it doesn't matter what order you put them in. So yeah, if the bounds are constants, put them on the outside. If the bounds involve variables, you need to resolve that integral before you get to that variable. So I need to resolve the x integral, which is determined in terms of y, before I get to the y integral, right? So that means that x has to be done before y. And if the y bounds had a z in them, if this was a z here instead of a 1, I would be forced to do the y before I did the z. Because otherwise, you'll see, if you just work it out the other way, you'll see that in your final answer, you won't get rid of the z's. You'll have a z in the in the final answer, but you should be getting a number as an answer. So you'll see it just doesn't work. If a variable appears up here, you need to do this integral before you do that integral, the integral corresponding to that variable. So I think that's the rule the general rule that we're using here. Now, if it's a constant, well, you don't have to worry about that because there is no variable here. So you can do those in whatever order you want. So I think that's the best way I can explain it. And it doesn't have anything to do with what this function is, by the way. This function could be anything. And what I'm saying for the other stuff, what I'm talking about is just the relationship between the bounds and these. Okay, this has nothing to do with what this function is. Any other questions? Can you repost the homework as we move on for practice? Oh, you mean to practice for the exam? When is our exam? I should check the calendar here. The exam is in 2 weeks, isn't it? It's Thursday after next Thursday. Yeah. So yeah, I can do that. I can post the homeworks just like we had for the previous exams. Sure. And I don't remember if I mentioned this last time, but on the last exam, I had a couple problems where I wanted you to show your work. I'm going to do the same thing on this exam. I'm going to make those work problems worth more points, substantially more points. Like, so that's like, I don't know, like a fifth of the exam will just be the work. In this last exam, I had trouble getting my open math to do it. So it ended up just being a third of one problem. So it ended up being very little points attributed to your work. I want the work that you show to mean more. So I'm going to weight it so that it's substantial. So make sure that you can work things out by hand and do it that way. Just warning you about that. How do I grade the exam? Well, my open math did most of the grading since it was done online. But I did look through. So when you submitted work for those problems, I downloaded and looked at your work, and then based on that, I gave you credit for the work part. So my open math attributed part of the points on the problem to your response, and then it also left a little bit of points left for the work that you submitted. And I just went through everybody's exam and just looked at their work and then submitted a score based on what I saw. And by the way, you should look through those, and I left comments as well if there was an issue. So if you got it, you should look through your exams, and if you see a comment there, make sure you read it. Yeah, yesterday's video will be posted. I'm having, it's a little bit problematic for me to process these videos and upload them. It takes a lot of time, and I'm having, so I left my computer on overnight, and it was supposed to process some videos, and it didn't. I woke up and it was like, it was waiting for me in the morning, and it was like, I'll start when when you're ready for me. I don't know why it didn't do it. So it's taking longer than I had hoped. But yeah, I intend to post these videos. I just, I don't know how long it's going to take. And hopefully I'll get them done today. Any other questions? Okay, it looks like we're set for questions. So, okay, I'm going to end the meeting, and I'll see you guys tomorrow. Please practice this stuff. Also, look into the next section about cylindrical coordinates. We're going to be doing these three-dimensional integrals, but we're going to be incorporating polar coordinates into it. And when you do polar coordinates in 3 dimensions, they call those cylindrical coordinates. And we may also do spherical. I think that was another thing. So I think maybe it's I think the next section deals with both of those. So read into that so that you have an idea of what we're doing. Okay? So I'll see you tomorrow. Bye, everybody.